Hello everybody. I am Anil Gautham Chokkalingam, and along with my friend Aravindhan and Vijayaraj, I'm going to present about our project hand gesture based wheelchair control model for differently abled. The inspiration for our project was the urge to help the society in some way. One such way was to help the physically challenged people. The boon for such people is the wheelchair. The wheelchair is developing day by day. The modern wheelchairs come equipped with a set of motors to help run the wheelchair via a joystick. The joystick controlled wheelchair is a bit difficult for certain people to operate, mainly for the old and weak people. Certain countries are implementing lots of guidelines for buildings to improve accessibility for disabled. They do this by helping people by providing ramps and parking spots specifically to such people. Our approach is to control the wheelchair with simple finger gestures rather than the traditional joystick input. We obtain the visual input by means of a Raspberry Cam. This input is then processed by the Raspberry Pi. The Raspberry Pi then sends out signals to control a set of DC motors, which then determines the movement of the wheelchair. Let me now shift the focus to the components of our prototype. The first component is the Raspberry Pi. Though there were a lot of options available, we chose the Raspberry Pi due to its small size, low power consumption of averaging about 2 watts, a GPIO, the processing speed of at least 700 MHz, the support for Python and OpenCV. There are many flavors of the Raspberry Pi that are available commercially. We have chosen Model B with two USB ports, an Ethernet port, and an HDMI port. The next component is the Raspberry Cam. The Raspberry Cam is a camera module that has been designed specifically for the use with Raspberry Pi. It boasts of a lot of features like a 5 megapixel camera which is capable of even recording 1080p video. The video is recorded in H.264 format and can also be converted to MPEG-4 format. The next component is the L293D IC. It is a quadruple high current half-H driver IC. It can be used to operate the motor in two directions. Although in this project we do not use the reverse direction, it can be used in future models to provide the reverse direction option if possible. Without this, we will not be able to drive the RDC motor, which requires a minimum of 6 volts as an input. Let me now talk about how we get the input to the Raspberry Pi using the hand gesture recognition technique. In this technique, the user's hand gesture is taken as an input. It is captured using the Raspberry Cam. The image is then processed for convexity defect points. Using the convexity defect points, the number of fingers shown is calculated. The motors are then made active or inactive according to the input. The Raspberry Cam is placed at the end of the armrest facing upwards. This is done to improve the comfort of the user. The regular size of the image captured by the Raspberry Cam is of 2.5 megabytes. With this size, the processing time may take longer. Hence, we capture the image at a lower resolution. We use the WVGA format with 720p width and 480p height. This image size is lesser than 200 kilobytes. Our technique requires a continuous input from the user. In case the input is the same, our program does not process it. It detects the changes in the input and only then processes it. The next part would be explained by my friend Aravindhan Vijayaraj.
Hi, I am Aravindhan Vijayaraj and I am going to explain about how the hand gesture input from the user is translated into motor outputs. The user may either show one or two or three or four fingers as an input, and the captured image is stored in the Raspberry Pi. The captured image has to be processed to find the number of fingers that are shown by the user. For this purpose, we are using Python as the coding language and OpenCV as the image library. A sample image input with two fingers is shown in the diagram. This is the flowchart of the code that finds the number of fingers that the user shows as an input. First, the image is read and stored as a NumPy array and then converted into a grayscale. Now, the contours of the image are found using the OpenCV library function cv2.findContours. The largest contour in the image is extracted and its hull is drawn. From this, the number of convexity defect points is calculated by using the function cv2.convexityDefects. This is in a vector form and the length of the vector array gives us the number of fingers that the user shows as the input. These are the images that are obtained after processing the sample input image which was shown earlier. The image on the left side shows us the convexity defect points that are in the image, and the image on the right side is the convex hull of the image. Now let's look about how we control the motor using the Raspberry Pi. The number of fingers that the user shows as an input should be modified to run two DC motors. If one finger is shown as an input, it is interpreted as movement in the forward direction and both the motors are made to run at the same time. If the user shows two or three fingers, it is interpreted as right or left turn and only one of the motors is made to run, while the other is kept inactive. While turning directions, the motor which is active is only for preset amount of time so that the wheelchair doesn't make a 360-degree turn. The motors are controlled by using the GPIO pins of Raspberry Pi, but the output of the GPIO pins is as low as 3.3 volts and it is not enough to control a motor. Hence, we have used the L293D IC and the circuit controlling the motor is shown here. The input to the motor 1 are from the GPIO pins pin 4 and 17, and for the input to motor 2 are from pin 23 and 24. The GPIO pins are named in BCM mode. The input voltage to drive the motors is given to pin 8 of the IC. A motor in a wheelchair may use up to 24 volts and hence this IC will be sufficient for driving the motor. These are snippets of the code that we wrote to control a motor by using the Raspberry Pi. As shown, for a movement in forward direction, both the motors are kept active at the same time. For turning in right direction, only one of the motors is kept active for 4 seconds. These are the possible areas of development in our project. Our initial aim was to control the wheelchair by using a single finger through finger tracking. This can be achieved only by color tracking rather than object tracking. If this is implemented, this could be a boost to the people who are older, as it would be difficult for them to remember the correct number of fingers that should be shown for movement in the appropriate direction. Another area that you would like to improve is to reduce the time delay between the input and output. That is, to reduce the time taken to capture the image and realize it as a movement in the wheelchair. Our project deals only with simulated output. We aim to use relays and more powerful motors to actually be able to move a wheelchair along with its user. Due to financial constraints, we were unable to produce the result, but we hope to realize the real-time implication of our project in the near future. This is our individual contribution to this project. We would like to thank our professor, Dr. Sudeep Pasricha, for his constant motivation and help. We would also like to thank our friends for their support and encouragement. Thank you.